Good evening, everyone. My name is Carl. I've been at Citadel for just over a year. I've been working in finance since the last global financial crisis, so Google it if you don't know when it was, but it was quite a while ago now. I'm a little bit different from the rest of these guys who are on the C++ committee. No C++ inside out and back to front. I work as a day job on low latency options for Citadel. And what that means is I use C++ a lot, but I don't really know it absolutely inside out. But I do know how to use it to get the fastest possible speed and lowest latency out of our trading systems, which is very important for a trading company. I'd like to start off by making the claim that it's actually pretty easy to write fast, low latency, high throughput software. It's relatively easy to do that, to write it, to get it past a code request, or sorry, a code review, get it past a pull request, put it into production slowly, it'll look okay, do some benchmarking on it, it'll look okay. The problem is that once you actually test it on a very, very busy day, there's a good chance it's going to slow down. And it's not because your algorithm is fundamentally bad and there's some logical error, it's all the hidden things that bite you time and time again. And these are the usual suspects. I mean, hopefully not too much of this is surprising to any of us in this room, but it's the things like the allocations that you didn't realize were happening. Cache line trampling, TLB misses, branch heavy loops, all of these things that are not obvious from the code, but will hit you over time. Memory fragmentation as well, that's a pretty tricky one because in the first few hours of something running, maybe it's okay, but maybe later in the day, it starts to slow down. One of the things about trading is that the very last hour of trading in the day is one of the most busiest where you need to be as reliable as possible. And that's often when fragmentation can come and hit you as well. Also, I find this a little bit ironic that I'm speaking about low latency and I'm going to have to run through this as low latency as I possibly can to hit the 5 minutes, but we'll see how that goes. So, I mentioned actually earlier about the fact that C++ and modern C++ is about expressing intent. It is, and it's about expressing performance intent as well. So with modern C++, we get these wonderful things. So const expression, const eval, move semantics were absolutely huge as well from C++ 11. That was a bit of a game changer. Really, really helps to reduce the latency and speed up your code. Pushing things into compile time and also just being as memory optimal as you can. These are all good things. So where does C++ 26 come in? Very early days, but there's some super exciting language features in there. So SIMD is huge. Standard execution, you've already heard about just before. And static reflection, so the standard meta namespace as well. So what I'd like to do is quickly give some examples of those three. There are some other potential benefits as well that I can see, but it's very, very early days, so we'll keep an eye on those. Okay, so this is pretty standard code. You'll find it in trading systems, games, audio, just a scalar loop. We're just running through some code. So at a decent optimization level, do you think this would get turned into vectorized instructions? What do we think?
Yeah, it should.
Yeah, it should. Probably will. If you get the compiler suspects there's some pointer aliasing going on there or a few other bits and pieces, maybe you won't, but probably you will. But not always. So you might change the code. Something in the code somewhere else might change. You might bump the compiler version, you might compile to a different target, and all of a sudden it doesn't vectorize. Or code that didn't vectorize now does, and it crashes because it turns out that you had, well, why would it crash? Any ideas? Width bounds? Yeah, an alignment issue will catch you out. And I've had this in production before where all of a sudden it vectorized and crashed in production. It was super hard to figure that out because it was dependent on the data coming in. It wasn't something that would crash every time. So what can we do about this? Standard SIMD. So now, SIMD instructions, which SIMD stands for what? Single instruction, multiple data, indeed. They're a first-class concept. If you use them, you'll get SIMD instructions generated. First-class concept, it'll work with templates. It should work with other language features as well. So it's not going to necessarily speed up bad code, but it will keep good code running fast without any sort of surprises down the track that all of a sudden it stops working. Actually, a bunch of super cool things about SIMD which I can't go into right now because of obviously the time constraints. But yeah, check this out. This is a very feature-rich SIMD library. Standard execution you've heard about, but it struck a little special part of my heart when I saw this the other day, because I have had to write exactly the same thing as Gasper has written as well, like for digital assets, doing a whole bunch of HTTP paging. My implementation was the worst code I've ever seen in my life, despite trying really, really hard to do this. Super inefficient, allocations all over the place, cancellations are super, super hard. Having something like this a couple of years ago when I was doing this would have been a game changer for me. And having something like this means that it's going to be relatively optimal and not unexpectedly slow down the track, because all of a sudden allocations are happening or something like that. Final point, or final example, and again, an absolute game changer, is static reflection. So in finance, in gaming, in audio software, well, mostly gaming and finance, I should say, there's so much deserialization of data coming off the network card or coming off the wire into C++ types, and then again back out to the exchange or to other components. And at the moment, the state of the art is using some sort of Google protocol buffers situation where you have your classes kind of defined in some interface definition language and having a third-party tool generate your code for you, or X macros, or some really, really crazy template tricks. Whereas now, or very soon, by the way, this is an artistic interpretation of what the legitimate code may look like, because it's still a working draft at the moment, as far as I know. Now you have absolute first-class concept of static reflection. So you can take any type, enumerate the fields, figure out what the types are, and so from there you can see it's relatively easy to generate a serializer, deserializer, a logger, a generic logger, or whatever it is that you want. The benefits here is that you're not going to generate a huge amount of boilerplate code, which is what code generators do, right? You can have generic functions that just get past the type and can compile time reflect. I don't know if anyone noticed that, but this is a conceval function. This is all at compile time, which is super cool. No runtime overhead. And you should be able to generate really efficient code from this as well. So it's just basically a game changer for, I think, a lot of people in this room, to be honest. And just from an ergonomics point of view, no build pipeline, no third-party tools, no multiple copies of the same thing, potentially different definitions because something's gone wrong with your build process when you're trying to generate these classes. And if you change a struct or a type, that's it. There's nothing else to do. Your code is automatically up to date. So yeah, again, something super cool. Helps you write code that probably isn't going to regress and slow down. So to finish up, C++26 is really helping us write low latency, high performance code. However, there's a caveat. These things here, so if you're not using user space networking, if your network isn't efficient, if you're not aware of NUMA and allocating memory to the right nodes, all of these sorts of things, if you haven't done that, then don't worry about the previous 6 slides. You have to sort that out. But once you've sorted that out, everything else that I've mentioned comes into play. So I guess the main thing I want to say in closing here is that C++26, it's not going to make a slow system fast, but it's going to help you from accidentally making a fast system slow. Thank you.